These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the annotation. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the annotation. Thank you. So let's try this problem.
Okay.
You can work that out on your screen.
Okay. A over B equals C. C times B equals A. A over C equals B. Okay.
Okay, that was correct. That was correct. Good. I'll go back to my screen. How did you go from this line to this line?
I just multiply both sides by B.
Okay, excellent. That's a good approach. Another approach you could use is cross multiply. If you cross multiply, what would you get?
Okay. A equals CB.
Which is the same thing. I'm not saying that's better. I just wanted to point out that's an alternative approach. Instead of saying you're multiplying both sides by b, you could say you're cross multiplying. You can cross multiply when two fractions are set equal to each other. So either of those is fine. The way you described it is perfectly okay. Now, how did you go from the second line to the third line?
Okay. We divided A by, I divided both sides by C.
Okay, excellent. Good.
Yep.
That's a good approach. I just wanted to point out that another approach that you could use is multiply both sides by 1 over C.
Okay.
When you do that, what do you get on the left-hand side?
A over C.
Because that's how you multiply fractions. And what do you get on the right-hand side?
CB over C. And then that cancels out to just B.
Right. So hopefully we could, that's the reason why it's a good idea to multiply by both sides by 1 over C. You could just cancel right here. You could just say, what's 1 times C? What's 1 divided by C times C?
Oh.
What is 1 divided by C times C?
1.
Yeah, so those cancel out. All right, I'm not saying that that's a better approach necessarily, but that's another approach you should keep in mind that you could also be using there. So the way you did it was perfectly fine. Sometimes it helps to think about it that other way that I just mentioned. Okay, good. So you got that correct. That was good. Let's do this on my screen.
Okay.
Can you think of any way to rewrite this expression? What's a way to rewrite this expression?
We can rewrite it as A, B, C, D.
Okay, that's perfectly good. Yep. Anything else?
Let's see. 1 over A, B, C, D, all raised to the negative 1. I think that's legal.
Like this?
We need some parentheses around A and D.
Like this?
Yeah.
Okay, great. Yeah, very good. That's another possibility. It was kind of a weird question. There's many different ways you could rewrite this. That's a perfectly good suggestion. How about this? Is this legal?
Yep.
And how about this? Is that legal?
It is.
Okay, so that was what I was going for here, but your suggestions are perfectly fine as well. This is called what's called multiplication is commutative. Multiplication is commutative. The order of multiplication doesn't matter. So that'll turn out to be important today. Oftentimes it's helpful to rearrange who's next to who when you're multiplying. Instead of having the A next to the B, maybe it would be useful to have the A next to the C. So it's often useful to rearrange the order of multiplication. So what would be a way to rewrite this expression?
Okay, so we can rewrite this as AB plus AC in parentheses, the whole thing. Yep, times dE.
Okay, excellent. That's a very good suggestion. You could use the distributive law. That's a good point. You could use the distributive law here. Okay, that's excellent. That doesn't turn out to be quite what I was going for, but that's a very good answer.
Okay.
What about this? Is this legal?
A times D times BC. Yep, that's legal.
How about, is this legal?
G times. Yep.
So my point is, again, just to hammer home this idea that multiplication is commutative. Multiplication is commutative. You can rearrange the order in which things are being multiplied. Maybe it's convenient to have the B plus C next to the E, or maybe it's convenient to have the D next to the E. So it's just good to keep in mind that multiplication is commutative. Okay? So the suggestions you were making were correct as well, but what will turn out to be important in this section is the idea that multiplication is commutative.
Okay.
Can you think of any way to rewrite this expression?
Let's see. We could rewrite this as A over D times B over E times C over F.
How do you know that's legal?
Because when we multiply these fractions, we get A, B, C over D, E, F.
Excellent. So you can check that by multiplying. Okay, good. All right, so that's a perfectly good suggestion. That's a perfectly good suggestion. That's totally legal. What about this? Is this legal?
Let's see. Yep.
How can you tell?
Because when we multiply this out, we get the same, the same starting product.
That's right. If you multiply them using the rules for multiplying fractions, you'd get back to what you started. So this is the approach that turns out to be helpful for the problems we'll be doing in this section. So the suggestion you made earlier was perfectly good, but for this section, this will be the way that's more useful to think about it. So the point is, notice that each term can be separated out. So the key point here is this is something that you kind of already knew. Dividing by a number is the same as multiplying by its reciprocal. Dividing by D is the same as multiplying by 1 over D. Dividing by E is the same as multiplying by 1 over E. And dividing by F is the same as multiplying by 1 over F. We'll see that'll tend to be a useful trick in some of the integrals that we're working on. So the thing is, we've seen that oftentimes before you can differentiate, you need to use algebra to re-express an expression. And also, oftentimes before you can do an antiderivative, you need to use algebra to re-express an expression. Well, these are some of the algebra tricks that we're going to need in this section to re-express some of the things that we'll be talking about. Okay? Can you think of any way to rewrite this term?
We could rewrite this as 1 over x to the negative 4.
Excellent. All right, very good. We've seen many times how that's a useful trick.
We could also...
Now, yeah, go ahead. Go ahead.
Okay, sorry. We could rewrite this as x squared times x squared, or x times x cubed, or x times x times x times x.
Outstanding. Excellent. So there's tons of ways, right? So it's hard to know what I'm going for here because there's tons of ways, but those are all great expressions. Those are all great. In fact, you picked out the one that we need in this section. This is the one that will be useful in this section. In this section, it's useful to break out one of the x's from the multiplication. In this section, it's going to be useful to just break out one of the x's. So all those suggestions you made were very good. I'll write down the one that will be useful to us in this section, which is this. How can you see that this is correct?
Because when we multiply x cubed times x, we get x to the 4th.
That's true, because what's the exponent on x?
1.
And how do you multiply two numbers with the same bases?
You add the exponents.
And so you can see that's correct. Okay, so all the suggestions you made were good ones. This is the one, though, that will be useful to us in this section. So that's one that is particularly useful to keep in mind. So using the same trick that we just talked about, how could we rewrite this?
Okay. Y times y to the 7th.
That's right. We can rewrite it like this. Good. There's many ways that you could rewrite it, but that's the one that'll be useful in this section. In some areas. Not every time, but sometimes that'll be useful.
Okay.
How could we rewrite this?
Secant of theta. Let's see. Secant 1 over cosine of theta.
That's actually the definition of secant, but that's good. That's good. Sorry, not a criticism. That's a good way to re-express it. That's exactly what I was going for. Good. So one way to re-express this is just to use the definition. So that's what I was going for here. That's good that you remember that. Remember, we've seen in the past that sometimes we've made mistakes because we confused secant with sine. So it's good that you didn't do that here. Secant is 1 over cosine of theta. Okay, I just wanted to review that important idea. That's good. Now, how about tangent of theta? Well, this one I'm just going to tell you because you and I haven't talked about this before. What's the definition of secant theta? The definition of secant theta is this, 1 over cosine theta. We've talked about that quite a bit. We never talked about what the definition of tangent theta is. It turns out that this is the definition. You might have seen this occasionally in class. But anyway, this turns out to be the definition of tangent theta. We haven't had to talk about this before because your calculator has a key for tangent theta. So you can just find tangent theta on your calculator. Why don't we check this, though? So use your calculator to find the tangent of 3.
Tangent 3. Tangent 3 is negative 0.1425.
So you use the tangent key for that?
Yep.
Great. Now let's check that using this expression.
Okay.
So you can tell me what you're typing into your calculator.
Okay, so sine of 3 divided by cosine. Sine of 3 divided by cosine of 3. And we get the same answer, negative 0.1425.
Okay, so we just proved that these really are the same thing. Very good. This is something you and I haven't talked about, but it'll be important for us in this section. Okay, so what's our new expression for tangent of theta?
Sine over cosine.
Sine of theta over cosine of theta. Good. So to review, what's our new expression? What would be the expression for the tangent of x?
It would be sine of x over cosine of x.
What would be an expression for tangent of t?
Sine of t over cosine of t.
So notice you can't just say sine over cosine. You have to say sine of a variable over cosine of the variable. Okay, good. All right, that's some new material that we'll need in this section. By the way, would you agree that you could rewrite this? What was I going for here?
Sine times secant.
Would you agree that we could rewrite this like this?
Mm-hmm.
Now they're two separate terms. And as you're saying, you could go even further and now change this into secant. I'm not going to write that down because it turns out that won't be something we need in this section. We won't need to do that in this section, but we might need to rewrite it like this. Okay, good. All right, now you and I have really hardly ever talked about this term. Do you know what COT stands for, what the word is?
It's cotangent of theta.
Yeah, so this is the cotangent of theta. Cotangent of theta. We haven't talked about what this means. We haven't talked about this very much, but it's kind of like secant. Secant is 1 over cosine.
Mm-hmm.
So what is cotangent? Cotangent is 1 over tangent.
Okay.
I think that's not too hard to remember from the names. Easier than secant, probably. So cotangent kind of sounds like it's derived from tangent in some way. So the cotangent of theta is 1 over the tangent of theta. And what's the tangent of theta? What could I plug in for the tangent of theta?
For the tangent of theta, we could plug in sine of theta over cosine of theta.
Now, though, we have a fraction inside of a fraction. So
Right.
try simplifying that on your screen. What does that simplify to?
So you multiply by the reciprocal. So, okay.
Okay, that was very good. Good. I'll go back to my screen. So we've talked about how to simplify those complex fractions before. Instead of treating them like a division, we treat it as multiplying by the reciprocal. So what that means now is we have a smaller expression than for cotangent of theta. What's our expression for cotangent of theta?
It is cosine of theta over sine of theta.
Notice, compare this with this.
Right.
So the cotangent is just the reciprocal of the tangent. Tangent is sine over cosine, cotangent is cosine over sine. This is actually going to be more useful to us here than this. The only reason I wrote this down as 1 over tangent theta is because I wanted to show you how it's similar to secant. I wanted to show you how the definition of secant as 1 over cosine is similar to the definition of cotangent as 1 over tangent, but this is actually not the expression that will be most useful in this section. The most useful is the cosine over sine. In fact, to hammer that home, let's just erase that stuff that we won't need for this section, and we'll just write it like this.
Okay.
So for this section, we can just say tangent is sine over cosine, and cotangent is cosine over sine. So that'll be an expression that we need for this section. Okay? And then would you agree that you could rewrite that as this legal?
Yep.
Yeah, so that might be useful as well to separate these into two separate expressions. Okay, so what's an expression for this?
Okay. Cotangent of x is equal to cosine of x over sine of x.
How do you know? Well, we just memorized it. We just have to memorize that. Good. How about this?
Let's see. Tangent of a. It's opposite. So sine of a over cosine of a.
Because we just memorized that. Good. How about this?
Cotangent of t.
Yeah.
Okay, that's cosine of t over sine of t.
Okay. All right, so those are just some expressions that we didn't need before in trig, but we'll need in this section. So we have to have those memorized. We have to have memorized what sine and cotangent are. Just as a memory aid, you might notice that cotangent starts with a C, and on the top you have cosine that has a C. Just remind yourself that for cotangent, it's the cosine that's on the top. And then the tangent is the opposite of that, just as a weak little memory aid. Okay,
Yep.
Good. All right, so these are a couple. So far we haven't done any calculus. What we've been doing is first we reviewed some algebra that we needed for this section, and now we reviewed some trigonometry that we need for this section. I think that takes care of the algebra and the trigs, and then we can start looking at some calculus. One thing we've seen in the past is when we were doing derivatives. When we did derivatives, first we learned a bunch of simple derivative rules. First we learned some simple derivative rules, and then we also learned some situations where the simple rules don't work. The simple rules only work in simple situations. So for example, is there a simple rule for finding this derivative?
Right, we use the power rule.
Yeah, and what would the power rule give us here?
5x to the fourth.
That's good. And that's good you mentioned that's the power rule. So does the power rule apply in this case? Yes, the power rule applies to that case. Does the power rule apply directly to this expression?
It does not.
Because it only applies when there's just an x.
Right.
When there's a whole expression being raised to a power, you cannot apply the power rule directly. So in this case, the power rule does not directly apply. Okay, very good. Does that mean we're helpless and we have to give up? Well, no, because we learned a trick. We learned that the way to solve this is by using the chain rule. And remember, the key to the chain rule is to substitute in a u into this. So we could use the chain rule to simplify this, but the power rule doesn't apply directly. Is there any simple rule for taking this derivative?
Yep, that is 1 over x.
Okay, good. That's just the simple rule for the derivative of a natural log. Does that simple rule for derivatives of natural logs apply here?
It does not.
So can we just say this is 1 over x to the fifth?
No.
No, that would be the mistake of applying the simple rule. You'd have to use the chain rule again here. The simple rule doesn't apply. That doesn't mean we're helpless. It just means that first we have to use the chain rule, and then we can apply the simple rules. Okay. Now, it'll turn out that the same thing happens with antiderivatives. You and I have been going over a bunch of simple rules for finding antiderivatives. But those simple rules only apply to simple expressions. The simple rules only apply to simple expressions. They don't apply when the expression is more complicated. When the expression is more complicated, we'll need new tricks, and that's the point of section 5.5. Section 5.5 is going to introduce one new trick, kind of like the chain rule, that can simplify antiderivatives that are too hard for us otherwise. So, for example, okay, so let's see. Can you take this antiderivative?
Yep, the antiderivative is 3/5 x to the fifth plus c.
That's good that you remembered the plus c. Excellent. So what you used there was the power rule for antiderivatives. The power rule for antiderivatives applies in that case. Does the power rule for antiderivatives apply here? Well, you and I haven't talked about this, but you might be guessing from my lead up here that no, it doesn't. The power rule only applies to simple expressions where you just have a single variable raised to an exponent, just like for derivatives. Just like the power rule for derivatives only applies to a simple expression where the base is just one variable, the power rule for antiderivatives is similar here. So the power rule for antiderivatives does not apply to this expression. So perhaps there's other tricks that we could use to solve this, but we can't use the power rule. Let's see, to make this more similar to this section, I'll write it like this. So still here, the power rule does not apply because we have an expression of x rather than just x here. So the power rule for antiderivatives would not apply in this case. Let's see, one moment. That wasn't a great example. Okay, again, the power rule for antiderivatives would not apply here. So we'll need some other tricks for working this out. Okay. Do we know how to take this antiderivative?
Yep, the antiderivative is negative cosine of x plus c.
Excellent. Now, can we use our same simple rules to take this antiderivative?
No.
No. We haven't talked about this much, but if you see the pattern here, the answer is no. You can't just use the simple rules. The simple rule for the antiderivative of sine only works when you're just taking the sign of a single variable. It doesn't work when it's the sign of something times a constant. So the simple rule doesn't apply here. That doesn't mean we're going to be helpless, but we're going to have to learn a new technique for dealing with this type of situation. Okay, so we can see here the pattern that there's some antiderivatives we know how to find, and there's also some antiderivatives that we don't know how to find. Do we know how to find this antiderivative?
Yep, it's sine of x plus c.
So do we know how to find the antiderivative of sine?
Yep.
And do we know how to find the antiderivative of cosine?
Mm-hmm.
Do we know how to find this antiderivative? Is this something we've talked about so far?
It is.
What do you think this would be?
Or maybe not. Hold on 1 second. Let's see. What gives us... Yeah, no. Yeah, I guess we haven't talked about this.
We know how to find its derivative, but we don't know how to find its antiderivative. Again, this won't be impossible, but we don't know it yet. We'll need new techniques from this section. So have we learned how to find the derivative of sine? I mean the antiderivative of sine?
Yep.
And cosine?
Yep.
Have we learned how to find the antiderivative of tangent?
No.
No, not yet. That's something that we're going to have to go over now in this section. That's something that we hadn't learned previously. Okay, good. What's this?
It's 12x cubed.
Using the power rule.
Mm-hmm.
So the power rule applies there. Does the power rule apply directly here?
I don't believe so, no.
How can you see that it doesn't?
Because we're taking the derivative of 3y to the fourth with respect to x.
So the point is the variable on the top doesn't match the variable on the bottom.
Right.
So our simple rules only our simple rules only apply when the variable on top matches the variable on the bottom. So in this case, the power rule doesn't apply. Now that doesn't mean we're necessarily helpless again. Again, we could use the chain rule here to rewrite this so the variables do match. But until we use the chain rule, we can't find that derivative. How would you calculate this derivative?
Okay. So we would have to use the chain rule. Oh, wait. No. Okay, so this would just be 6x cubed.
So what should I write down here?
6x cubed.
What's the exponent here?
I mean squared.
Okay, squared. Okay.
Yeah.
So let's talk that through. But wait, how can you take the derivative when the top variable doesn't match the bottom variable? Well, you can't, but you can just use simple substitution to fix that. What does y stand for in this problem?
Y equals 2x cubed.
So we can just use simple substitution, and now the variables do match. Now the variables do match, and now you can use the power rule. So notice in this case, we didn't need the chain rule. The chain rule is a way of changing the bottom variable. The chain rule is a way of changing the bottom variable, but we didn't need that. We could just change the top variable in this case. So we said you can't take derivatives when the variables don't match. You can't take derivatives when the variable on top doesn't match the variable on the bottom, but that doesn't mean that you're at a dead end. Oftentimes it's easy to make the variables match by just using simple substitution. How would you work out this derivative?
Okay. So this is 20t to the fourth.
Now, the variables don't seem to match. So how did you find that derivative? Well, hopefully you said to yourself, I can substitute in for a. What could we substitute in for a?
4t to the fifth.
What's the advantage of that? The advantage is now the variable on top does match the variable on the bottom. And now, what was the answer?
I believe 20t to the fourth. Yeah.
Now we can use the power rule. Okay, good. So the point is, you cannot take a derivative unless the variable on the top matches the variable on the bottom. What do you do if the variables don't match? Well, you might use the chain rule to change the variable on the bottom, or, much easier, you might just use simple substitution to change the variable on the top, so the variables do match. So what's this? Can we take this antiderivative?
The antiderivative is 1/3 x cubed.
Plus c. Good.
Yep.
Can we take this antiderivative? Can we apply the power rule for antiderivatives here?
Nope.
Why not? Because now the variable inside the integral doesn't match the d variable. This is something you and I haven't talked about before. We haven't really paid much attention to this d variable for integrals. We've said that this means the integral of x squared with respect to x, and this is the integral of x squared with respect to t, but we haven't really said, we haven't used that for much, but now we're going to need that more. We're going to be paying more attention to this d variable here at the end. So here we can't take the antiderivative yet. Again, it doesn't mean that we'll be stuck, but we're going to have to do something to make these variables match. Probably use substitution. We're going to have to use substitution to make the variables match. You can't take the antiderivative until the variables match. So what's this?
Okay. So we can't go on yet.
Yeah, all right. So I was trying to trick you into saying negative cosine theta. But that doesn't work here. We can't do anything yet because the variables don't match. So we can't take this antiderivative yet. We're going to have to do some work to make the variable here match this variable. Only then can we take the antiderivative. All right. Okay, so is this an antiderivative that we know how to take using our previous techniques?
Let's see. I believe so. I think we can distribute the x squared and then take the antiderivative. So cosine of x. Yep.
And then what?
So now we can take the antiderivative and next I would rewrite it as cosine of x to the fifth plus 3x cubed.
So it sounds like you did this.
Yep.
Why? How can you tell if that's legal or not?
Well, that's not the antiderivative. I was just going to rewrite.
Good point. How can we tell
sorry.
whether it's legal to put the x squared? So is it legal to put the x squared in the parenthesis?
No, I don't think so.
Okay, no. So I guess we can't do that.
Okay.
So you were going to say this was cosine of x to the fifth.
Right.
But that turns out not to be legal. What you were probably thinking of is something like this. This is legal. You can put the x squared inside of this parenthesis. But this is not legal. We talked about this a while ago in a previous session. These are two different types of parentheses. This parenthesis just means multiplication. Well, you can move this term inside the multiplication parenthesis. But this parenthesis, does not mean multiplication. It's a function parenthesis. There's no, unless we have some justification, we can't just move terms in and out of cosines willy-nilly.
Okay.
So that's not going to be legal. Okay. Well, so it turns out that, in fact, this expression is much too complicated for us to solve, for us to integrate using the techniques that you and I have talked about previously. Using the techniques we talked about previously, this is way too complicated to solve. So we're going to have to use a new technique now for this problem. And I'll just show you the new technique. The new technique is integration by substitution. So here we're going to use the integration by substitution technique. The hard part here is knowing what substitution to make. Did I write this down correctly? 1 second. Maybe I didn't even write this down right. Okay. Yeah, I didn't even write this down correctly, so it wasn't really a fair question. Let me write it down like this. I was leaving out parentheses. This is really what I meant to write. Okay, so what I wrote down before didn't make much sense, but we don't know how to solve this either. We don't know how to solve this yet either. So what I had down before wasn't really what I meant. But in any case, here's what we're trying to solve. So we're going to use a substitution. Now, how do you know what to substitute? Well, you want to make a substitution whose derivative is also in the function. You want to make a substitution whose derivative is also in the function, or at least up to a constant multiple. Make a substitution for a term whose derivative is also in the integral. Up to a constant multiple. So we'll have to look at an example to see what that means.
Okay.
Have that down?
Yep.
So here's the substitution we're going to make here. Well, what's the derivative of x cubed plus 3?
That would be 3x squared.
So notice its derivative is already here in the expression. The derivative of x cubed plus 3 is 3x squared. Well, there's already an x squared here in the expression. Now, this derivative would be 3x squared, but that's okay because we said it only had to match up to a constant multiple. The 3 doesn't really matter. What matters is the x squared. So it turns out that the substitution to make is this one. U equals x cubed plus 3, because its derivative is in this expression. Okay, and we'll have to look at some examples to see how this works, but now we could rewrite that as So how can we simplify this expression now? using our
so
substitution.
we can rewrite this as x squared times cosine of u with respect to x.
Dx. Okay. You can see we've already made progress because this looks simpler than what we started with. We've made progress because now this looks simpler to what we started with. Instead of the cosine of a big, complicated expression, it's just the cosine of one variable. But we have a problem here, which is now we have two different variables, x and u. Remember, that's not acceptable. It's not acceptable to have two different variables. We need to have only one variable inside the integral. Actually, now that I think about it, I didn't quite say that before, but I'll say it now. We can't take the antiderivative until there's only one variable in the antiderivative. We need to have only one variable here. So now here's where the next trick comes in. What's this?
Du over dx. So we take the derivative of the inside function over the derivative of the outside function.
Sounds like you might be overcomplicating that. What does u stand for?
The inside function.
Let's see. In a way, it does. Now, remember, we're not exactly using the chain rule here. The chain rule is for derivatives, and we're doing an antiderivative. So even though this is similar to the chain rule, we're not doing the chain rule exactly. But what exactly does the u stand for here?
X cubed plus 3.
So do you see how we could do this substitution?
Mm-hmm.
So then what's the derivative?
3x squared.
Okay, so that's what I was going for. So what's the derivative of u with respect to x?
3x squared.
That's right. Okay, this is just that substitution technique for derivatives that we were reviewing earlier. Earlier we were reviewing this substitution technique for derivatives, like in this line here, or in this line here. So that's what we did here. In fact, this is something we can probably now start doing in our head. So I'll erase that middle term and just go straight to here. Okay. All right, and now we're going to do something new that we've never done before. In the past, we've always treated this type of expression as a single symbol. So we haven't really been treating this as a fraction. Even though it looks like a fraction, we haven't been treating it as a fraction. We've been treating it as a single solid symbol. But now we're going to break that pattern. We're now going to treat this as two separate symbols, du on the top and dx on the bottom. So if we treat this as two separate symbols, du on the top and dx on the bottom, let's solve this for du. What do you get here when you solve this for du?
You get du equals 3x squared dx.
That's right. Now we're treating the du and the dx as two separate symbols. That's something we never did before. Okay, and our goal here is to use this to simplify this expression over here. So now I'm going to take this expression, and would you agree we can do this? That this is the same as this.
Yep.
Remember, we can rearrange the order that we multiply things in. That's what we were talking about earlier today. If you have a multiplication, you can rearrange the order of the multiplication. So that's what we're doing down here. We've rearranged the order of that multiplication. Now what I want to do here is get rid of the x squared. I want to get rid of the x's here and replace this just with u's. We started with an integral about x. In order to use the substitution technique, we have to replace that with an integral about u. So I need to rewrite this so it's all about u.
Mm-hmm.
I'm going to try to use this substitution. These are already a pretty close match. I just need to get the 3 onto the left-hand side. So how can I rewrite this expression so the 3 is on the left-hand side?
You can write dx equals du over 3x squared.
That's right. You could do that. You could do that. That's perfectly legal. That's not quite what we're going to do, though, because I don't want to move the x squared. I only want to move the 3.
Okay.
How can I just move the 3?
We can rewrite it as dx times x squared equals du over 3.
That's right. You divided both sides by 3?
Mm-hmm.
Good. Maybe a slightly better way to do that is to multiply both sides by 1/3.
Okay.
So what's going to be on the left-hand side now?
du over 3.
Or let's actually keep it as 1/3
Okay.
times du. And what's going to be the right-hand side?
The right-hand side will be 3x squared dx times 1/3.
What does that simplify to?
It simplifies to x squared dx.
That's what I was going for. That's the whole point of multiplying by 1/3. It cancels the 3, and we get this. Now, what's the advantage of that? Well, remember, we needed to get rid of the x's here. Well, now we can get rid of all the x's in one fell swoop. I can get rid of the x squared times dx here and replace it with what?
1/3 du.
So that was the point of all those manipulations that we made here. The point of all those manipulations was to get something here that looked like what we had in the integral, so we could make this substitution. We wanted to get something here that looks like what we have in the integral, so we can make this substitution. And now we have an integral that's only about u. Now we have an integral that's only about u. And it's certainly a much simpler integral than we started with, so it might be easy to get lost here, but notice we started with a complicated, scary-looking integral, and by using a clever substitution, it's become much, much simpler. In fact, this is now an integral that we should know how to find. Why don't you try doing this on your screen? What would be this integral?
Okay, so the antiderivative of cosine. Let's see. Sine. This is 1/3 cosine. Okay.
Okay, good. That's right. Good. You paused there for a moment, but that was fine. You were thinking it out. That's good. So maybe a good way to write that is the first thing we should probably do here is this. Is this legal?
Yep.
That's the constant multiple rule for integration. Here we use the constant multiple rule for integration. And then you know how to take this antiderivative. I noticed you paused for a moment about what to do with the 1/3. You might have been asking yourself, do I have to take the antiderivative of 1/3? Well, that's something we talked about in the past. If we were adding the 1/3, we would have to take its antiderivative. But when you're multiplying by 1/3, you can just use the constant multiple rule and bring it out of the integral. You're not actually taking the antiderivative of the 1/3. Okay, so in a way we're done. Remember, we were trying to find this integral and we figured it out. But we shouldn't be satisfied with our answer yet because it has this new variable u in it. U is just a variable that we made up out of thin air. We're not allowed to leave that variable u in our final answer.
Right.
So how could we rewrite this now without a u?
We can plug in x cubed plus 3 into u, and now we have 1/3 sine of x cubed plus 3 plus c. And that's it.
Okay, that's right. So this is that antiderivative. Okay, so that's the substitution technique. It took us a while to talk through this because this was the very first time we did it. But with practice, it shouldn't be a super long approach. So that's so this is the last new technique for the course. We just have to learn how to apply this technique. It'll take a little work. But anyway, this is our first example. So now we've vastly expanded the range of expressions that we can take the antiderivative of. Before, we could only take the antiderivative of pretty small, simple expressions. But now we can take a pretty complicated looking expression like this and find its antiderivative. So let's go back and review the steps that we used here. First of all, this expression was too complicated to take the antiderivative of. So we decided to use the substitution technique. That was a pretty easy decision because that's the only advanced technique that we're going to know for taking antiderivatives. Now the trick here is make a substitution for a term whose derivative is also in the integral, up to a constant multiple. It might have been hard to understand what I mean by that, but hopefully this example should make it clearer. Why did I decide to set u equal to x cubed plus 3? Why not set u equal to x squared, for example? Well, what's the derivative of x squared?
It's 2x.
But that's not in the expression, is it?
Right.
We don't want to make that substitution because the derivative of x squared is not in the expression, and this technique doesn't work so well in that case. On the other hand, what's the derivative of x cubed plus 3?
3x squared.
And that is in the expression. Now you might object that the 3x squared isn't here, only the x squared, but that doesn't turn out to matter because of the constant multiple rule. All we need is something whose derivative is in the integral up to a constant multiple. It doesn't have to be there exactly, it just has to be in there up to a constant multiple, and then the trick will work. So this is the correct substitution to make because its derivative is here. Why didn't I put in u equals cosine of x cubed plus 3? Why didn't I say u equals cosine of x cubed plus 3? Well, I'm not exactly sure what the derivative of cosine of x cubed plus 3 is. It's kind of complicated, but whatever that derivative is, it's not here in the integral. So that was not the best substitution to make either. So then we made the substitution, and we can immediately see how things simplified. But notice that before we could do anything else, we had to get rid of all the x's. We have to replace all the x's with u's. That means we have to get rid of the dx and replace it with du. We have to get rid of the dx and replace it with du. In the past, we've basically been ignoring this dx term, but now it becomes very important. So here's the trick. The trick is take the derivative of u with respect to x. Take the derivative of u with respect to x, and then treat du and dx like they're variables. So we can cross multiply, and then try to rearrange this expression so all the x's are on one side and all the u's are on the other. Rearrange this so all the x's are on one side so it looks like what you're trying to get rid of. For example, here's what we were trying to get rid of. We were trying to get rid of x squared dx. So we solved this expression for x squared dx. We were trying to get rid of the x squared dx, so we solved this expression for x squared dx. And then when we did that, everything was all u's, and then we were able to take the antiderivative, and then we plugged in at the end. Okay, so that's the approach. Is that making any sense?
Yeah.
All right, so let's move on and look at another example. Okay, so the first thing we're going to try this antiderivative. So again, we'll work on this on my screen. Now, the first thing you should ask yourself is, do you know how to solve this using the simple techniques we studied earlier? Do we know how to solve this using the simple techniques we studied earlier? That can be hard to tell, but the answer is no. This is too hard to solve using the simple techniques we talked about before. So instead, we're going to use the substitution technique. Now, what substitution should we make? Well, remember, we want to make a substitution for something whose derivative is also in the expression, up to a constant multiple. So you might try, say, this, u equals x. Oh, well, that would be silly because that would hardly simplify things at all. If you just replaced u with x, that wouldn't simplify things at all. So that would not be a great simplification to make. How about u equals 3x squared minus, excuse me, next, 3x squared minus 2. Well, what's the derivative of 3x squared minus 2?
6x.
And that is here. There is an x. Now, It's not 6x, but that's okay. We only need it to be in there up to a constant multiple. So this is the substitution we're going to make. Why not do this substitution? Well, because the derivative of this is not obviously in the expression. This is a complicated derivative, but whatever its derivative is, it doesn't look like that's here in the expression. So we want to make a substitution whose derivative is in the expression. Okay, so then we'll rewrite it like this. So how can I now rewrite this so it has a u in it?
Okay, and we write this as x times the square root of u with respect to x.
That's right. Good. Now, I think the best thing to do now is rewrite this so all the u's are together and all the x's are together. So how can we rewrite this so all the x's are together? Well, we'll move the root u over here, and I'll move the x so it's next to the dx. And our next job is to get rid of this. We need to get rid of this and replace it with an expression in terms of u. Well, the trick is to go back here. What's du with respect to x?
Du with respect to x is 6x.
That's right. Technically what you're doing there is you're using substitution to get rid of the u. And now that the variable on the top matches the variable on the bottom, you can see the derivative is 6x. So that's such a simple technique, we don't need to keep writing that out. We can just go straight to here. Now what you need to do is rewrite this expression so there's an x dx on one side and the rest on the other side. So how could you rewrite this expression? You might try to do this on paper or on your screen, or how you like. How can you rewrite this so there's a, well, the first thing to always do is cross multiply. You always want to cross multiply. So what do we get when we cross multiply this?
We get du equals 6x times dx. And then
now we want to solve this for x dx.
Right. So now we can rewrite it as du over, or sorry, 1/6 times du equals x times dx.
Okay, good. And now, how can I rewrite this term?
Okay, so let's see. Now we can rewrite this as the integral of square root of u times 1/6 times du.
Okay. Now, is that progress? Yes, because now we have only u's. The goal is to get rid of all the x's. So notice, how do you get rid of the x's? It's a two-step process. First, we use our simple substitution to get rid of some of the x's. And then we use another substitution in terms of du and dx to get rid of the other x's. By the way, you can start to see now why we had to make a substitution whose derivative was in the integral. Otherwise, this step wouldn't work. We need to make a substitution whose derivative is in the integral so that we can get rid of all the x's at this point. Otherwise, we're going to get a hodgepodge of both u's and x's, and the technique won't work. Okay, well now we should be able to do this integral. So why don't you try this on your screen? Try taking this antiderivative now on your screen.
One half plus 1, 3/2, 2/3. So so I plugged you back in. Oh, we took the anti. Okay, I don't need this. Okay. Okay.
Okay, all done?
Yeah.
All right, now we still have to remember the plus c.
Ah,
Okay. Because we're taking indefinite integrals.
right.
If they were definite integrals, we wouldn't need the plus c. Okay, I think you took that antiderivative of the u correctly. I'll go back to my screen.
I kind of realized I skipped a step, but I didn't go back. But yeah, I should have rewritten the integral.
So probably at this point, it's still safer not to skip any steps and to rewrite it like this. Perhaps this is what you were thinking of. So we can use the constant multiple rule to take the 1/6 out of the integral, rewrite the square root as u to the 1/2, and now we have 1/6 times, I think this is what you got.
Mm-hmm.
Okay, good. Now there's a simple simplification that you could make here. What is 1/6 times 2/3?
1/9.
That's right.
Right. It's 2 over 18.
So you might want to make that simple simplification, although it's probably not necessary. And now the important thing is you remember to plug in for u. U was 3x squared minus 2. Okay, and now we can write that what we found was this indefinite integral. So again, we've really expanded the range of indefinite integrals that we can work out into things that are more complicated than what we were seeing before. Okay, so that's another example of that substitution technique. We recognized that we couldn't do this with our simple techniques. We made this substitution because we saw that its derivative was in the expression, at least up to a constant multiple. And then first we made one substitution to get rid of some of the x's, and now here's the tricky part. The tricky part is now at this point, rewrite it so all the x's are together. Put the x next to the dx, put the x next to the dx, and then try to use du over dx to solve for x times dx. And then we can get rid of that term. That's the tricky part here. By the way, notice dx is now we're treating that as a single variable. This is not d times x. Dx does not mean d times x. It's a single variable. Just like this does not mean the square root times 3. It's the square root of 3. This is d of x. But we're treating dx and du now as separate variables. Okay. Okay, well, those are a couple of examples, and now we can start trying to do these on your screen.
Okay.
So let's start trying to apply the same techniques to this problem.
Okay. So we can't take the antiderivative of this function. So substitution. So okay. I'm forgetting what to do with this x. Let's see.
So the useful thing now is rewrite the integral so all the x's are together and all the u's are together.
Okay, cool.
Now, so what's the term we need to get rid of in the integral?
The u?
No, we need to get rid of the x dx.
Oh.
Remember, we just put in the u, right?
Right.
We just put in the u. What we need to get rid of now is the x's. How are we going to, so to review, what's the term we need to get rid of in the integral?
The x.
X dx.
Right.
And we're treating now dx like a variable. Before we were just trying, so this is a little confusing because in the past we were treating dx like it was just like a right parenthesis. But now we're treating the dx as if it's an actual variable. So what's the term we have to get rid of? X dx.
Okay.
So to reinforce that, what's the term we have to get rid of?
X dx in this case.
So what do we need to solve for off on the right? We need to solve for x dx. Usually you solve for a single variable, but here we have to solve for that expression x dx.
Okay. Okay, so now I can take this and rewrite this. Okay.
Okay. All right, so that's another example then of this substitution method. Let's see. Okay, so let's review. Where did we get stuck here? Yeah, the start at the point that you just started. So you made, remember we get rid of the x's in two stages. First of all, you got rid of the 4x squared plus 2 by substituting in the u. But that still left us with some x's. So then the next trick that's helpful is rewrite the integral so the x's are all next to the dx. Rewrite the integral so the x's are all next to the dx. We can do that because multiplication is commutative. X times sine of u is the same as sine of u times x. So then what was the term, what was the expression that we had to get rid of in the integral?
X dx.
Yeah, x dx. So what was the, so off to the side you had du over dx equals 8x. And we had to solve that expression. Du over dx equals 8x. What did we have to solve that expression for?
For dx x.
The thing we were trying to get rid of.
Right.
We had to solve it. So notice you can't really, you can't do the work on the right until you've rewritten the integral to see what you need to get rid of. First you need to rewrite the integral to see what you need to get rid of, and then you go over to your du over dx expression and solve that for the term you're trying to get rid of. And then you're able to proceed. All right, I'll go back to my screen.
So I'm guessing these problems are set up so that they work out like this, because it seems almost like too much of a coincidence that
the derivative of 4x squared is an x, and that's already there.
Right.
Excellent. That's a very good point. That's good that you were thinking about that. That's a good point. So a moment ago, I was just boasting about how useful this substitution technique is and how it expands the range of things that we can solve. But what you just made, the point you just made is an excellent point. The technique that we just used would have been powerless to solve this expression.
Mm-hmm.
We don't know how to solve this expression because the derivative of x to the fifth is 4x third. I mean, is 4x to the fourth. But there is no x to the fourth in this expression. And the derivative of 4x squared is 8x, but there's no x by itself in the expression. So the substitution technique by itself can't solve this. So that's a good point. there's still going to be many antiderivatives that the substitution technique won't work on. There are many antiderivatives that the substitution technique does not work on. For that, you would need more advanced techniques. Those are usually covered. So other courses might cover those in the first semester, or they might be covered in the second semester. Usually, the second semester starts with a lot more techniques for integration.
Okay.
Usually the second semester starts with a lot more techniques for integration that we're not going to be getting to. But by the way, it's also worth mentioning there's also many definite integrals which are just impossible. There are there's many indefinite integrals. There's many antiderivatives that are just impossible to get an exact solution for. So there's some definite integrals that you can solve using substitution. There's some indefinite integrals you can solve using other advanced techniques. And there's also many antiderivatives that are just impossible to get an exact expression for. But anyway, the point you made is a good one. All of these problems are very carefully set up to make sure that substitution will work on them. You're absolutely right. If the problem was not set up carefully, you could easily get a problem where substitution would not work. So that was a good thing to observe. All right, so let me write down another expression here. Okay, let's try this one on your screen.
Okay.
I changed the minus to a plus.
Okay. Okay, so we couldn't the antiderivative. So we use substitution. And we set this to u as the derivative is a constant multiple of x.
Good. That's a good substitution because the derivative of 3 plus 5x squared is 10x. And that derivative does appear as x in the integral aside from the constant multiple. Good.
And now we rewrite this so x's are on the same side. And then we solve for x dx. We get 110 du, plug that in. Take the antiderivative and you plug u back in. Okay, well, we're good. I think.
Okay, so where's your answer?
Down here.
Okay. Excellent. For the final line, it's good to recopy the left-hand side to remind yourself what you solved for. So we'll get rid of the dittos on that final line and show what we actually solved for. You don't need to write it all over again. You can just erase the dittos you have up above and write down the expression.
Okay.
To remind ourselves what the point of that effort was. Good. Okay, very good. I'll go back to my screen. That was good progress on that type of problem. Very good. So I'll go back to my screen here. Okay, let's try this problem.
Okay. Well, the derivative. Okay, this would just be 3. Derivative this would be 1. So
I think you miscopied the problem. I made some changes as I went, so you might have ended up miscopying it.
3x squared minus 2. Okay, cool. Yeah. Okay.
As we were saying, these problems have to be constructed carefully to make sure that you can actually use the technique.
Okay. Okay. Okay, this is 6x. So du equals. Let's see. Sorry, my fan on my laptop is going crazy. I'm not sure why. Okay, so you got this. And I'll take the antiderivative. So 7, 1/7 to use 7. And okay, so use 3x squared minus 2.
Good. Now, since you already have the answer, You don't need to write a new line. You can
Okay.
just erase your last set of ditto marks and put the integral you were solving for there.
Okay, cool.
Okay. Well, that's good. That's good progress because, we haven't done a problem quite like this before. The problems we were doing earlier involved trig functions. This is the first problem that's quite like this, but you figured out on your own how to adapt the substitution technique to this new type of expression, and you did that correctly. So that's the important thing. There's many different places we can apply substitution, and you applied that correctly here. That was good. How can you check that answer? How can we check our answer here to see if it's correct?
Let's see. Well, we could take the derivative. Wait. Let's see. This is the antiderivative. Okay, yeah, we could take the derivative of what we found, and it should be the integral that we were interested in.
So what should be the derivative of 1/6 times 1/7 times 3x squared minus 2 to the 7th plus c? What should its derivative be?
It should be x times 3x minus 2 raised to the 6.
Okay. So let's check that this time. Let's check that and see how that works.
Okay.
That's good practice for us because so the only test you have left is the final, right?
Mm-hmm.
And so you're going to have to do a bunch of derivatives on that, I'm sure. So this is good practice anyway. We need to get back into the habit of doing tough derivatives again. I'm sure you'll see these on the test. So that's good practice for us here to practice our derivative skills.
Okay, so we need to check this. Okay. Okay. So we need to use chain rule. First, I'm going to rewrite this.
Let me give you a hint. Don't change it into 1/42.
Okay.
Leave it as 1/6 times 1/7. Even though it's legal to change it into 1/42, it'll actually be more convenient to leave it like this.
Okay, so let's do this. Okay, so let's see. You need to take this derivative. I definitely need to use chain rule. So I'm going to have something like this. Okay. And then this derivative is okay, I'm going to go with this. I wasn't quite sure how to handle these fractions up front, but I think I did this part correctly. I could be wrong.
So now what?
Okay, so now I need to check if this is the same. And it does not. 1 times 1/6. So this is
Do you see why it was a good idea not to put in the 1/42th? It was better to leave it as 1/7 because then the 1/7 canceled with the 7. Good. What's 1/7 times 7?
1.
Good. So those canceled.
Okay. This part looks the same. 6x. Okay, yeah, that's the same. This is, I think. The only part that looks a little funky is 1/6. Maybe I'm missing something. Huh.
So let's see. So first of all, we're not trying to match up to the dx, right?
Right.
The dx was just part of the antiderivative notation. Did you say the 6x matched up?
Oh, okay. Yeah, then that makes sense. So 1/6 times 6x is just x. So x times 3x squared minus 2 raised to the 6. And yep.
So it's a perfect match.
Right.
And you can see why we didn't want to do the 1/42th, right?
Mm-hmm.
Because the fractions are going to end up canceling nicely this way regardless. Okay, so that's a good exercise here. That's good practice with taking derivatives. That's good that you saw that we had to use the chain rule here. We haven't done a chain rule problem for a while, so it's good that you remembered how to do that. I think I'll go back to my screen. So we did get that problem correct. So here's the derivative that you were taking. So we've talked in the past about how it's useful when you're in doubt to take smaller little baby steps. So what we could do at the start here so far I've just used the sum rule. And what's the derivative of c?
0.
So that term drops out. So I think you had mentioned that you weren't quite sure how to deal with these fractions. You did deal with them correctly, but here's how we could boost our confidence. Notice that what we're doing here is we're using the constant multiple rule. We're using the constant multiple rule because these are just constants multiplied times the other expression. So we're using the constant multiple rule to pull these out of the derivative. We use the constant multiple rule to pull those out of the derivative, and then we can use the chain rule. These are not really involved in the derivative anymore. I must have messed up somewhere.
Was it to the 6th power? Oh, it was? Okay. U to the 6th.
It should have been to the 7th power. I put in the exponent from the problem rather than the exponent from the answer, so I got confused. I was trying to show you how to get less confused, but I got more confused myself. So I was trying to help you to get less confused with how you solved it, but I was the one that was confused here. So I'm not checking the original problem, I'm checking your answer. So your answer had an exponent of a 7 in it, so that should have been a 7. And this should be a 7. And this should be 7 u to the 6th, 7 All right, that looks much better. Okay, and now you can say 1/7 times 7 is 1. And we can rewrite that now like this. The thing that was giving you trouble here at the end was not seeing that we can cancel the 1/6 and the 6. That was the purpose of what we were talking about at the beginning of the session today, about how when things are multiplied, you can rearrange the order that they're multiplied in. When things are multiplied, you can write the order that they're being multiplied in any order that you want. That's what was helpful here. It helps here to write the 1/6 right next to the 6. Then you can see they can cancel, because what's 1/6 times 6?
1.
And then that drops out. And now we can see we really did get back to what we started with here, did we? X times 3x squared minus 2 to the 6th. We really did get back to where we started, so that confirms it was correct. Okay, well, I managed to confuse myself here a little here, but I wanted to do this because you had mentioned you weren't quite sure how to deal with these fractions. So I wanted to show what you were really doing with the fractions was using the constant multiple rule. You were using the constant multiple rule to take the fractions outside of the derivative. And if that's not clear, it helps to use the constant multiple rule first and then do the chain rule. I think the way you confused yourself is you tried to use the constant multiple rule and the chain rule at the same time. You were a little confused because you were trying to apply the constant multiple rule and the chain rule at the same time. But if we first apply the constant multiple rule and then apply the chain rule, I think we can have more confidence. And then we can see that we did that correctly. I'm not saying you have to include every single step here when you do these. You don't have to include all these steps. But if you're not sure of yourself, then it's better to include more of these steps. In any case, we ended up, and then we also saw how we can rearrange the order that things are multiplied in to see that the 1/6 is going to cancel the 6. Okay, so we saw this this came out correctly. Okay, very good. So you did that problem correctly the first time, and then you were able to check it. Let me write down another problem here.
Okay.
Let's try this problem.
Okay. Okay. So. Okay. Antiderivative of E of U. Okay. All right, I gotta write this. Okay.
Okay. How could you check that answer?
You can take the derivative of what we found. Should equal the integral. So we'll do that.
So if it's correct, what would the derivative equal?
X times e to the 4x squared.
That's right. Okay, so let's check that.
Okay. 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 So now we use chain rule. So e to the u times well, masses.
Excellent. Very good. Okay, that's exactly right. Good. I'll go back to my screen. All right, well, that's the first problem that we've done using this technique and using the e function, but you figured out how to adapt to that type of problem. So that's good. I'll go back to my screen. Now let's try this problem.
Okay. Okay. So Let's see. So okay, yeah, okay, I think I see. One over x times dx, dx over x. Okay, so we need to get 1/2 x and dx. So we need to get 1 over x and dx. So let's see. Wait, I should just leave it like that then. Okay. Oh, okay. I can plug in here. And now, let's see. Okay, I think that's good.
Okay, let's check that answer.
Okay. Okay, so go ahead and pull this out. So I'm going to use, let's see, I'm we take the derivative. This derivative is going to be 2 to the 4th. And 4. And then now we need to use chain rule. And u was natural log of x. Okay, so now this cancels out and get 1/5 and natural log of x cubed plus 1 over x is equal to natural log of x cubed over 5 plus 1 over x. This part matches up, but this wasn't an integral. 1 over x wasn't an integral. Derivative of x with respect to x, but I guess that's just because we had to use chain rule, that's why it's there. Okay, I think it's good. I'm not 100% sure why this is there, if this is the correct answer, but
So what did we want this derivative to come out to equal?
we wanted to come out to equal the natural log of x cubed over 5x.
Okay.
I mean, over 5, yeah. Oh, okay. Gotcha. Wait. Yeah, I think I made a mistake then.
So what did we want the derivative to come out to equal?
The natural log of x cubed over 5x.
I think you were forgetting that x with the 5x. Anyway, you use the chain rule here. When you use the chain rule, you have to do the derivative of the outside and what else? Derivative of the chain rule is that the derivative is the derivative of the outside.
And the derivative of the inside.
Well, what does the and stand for? Derivative of the outside.
And the derivative.
But and is not a mathematical
term.
It's the derivative of the outside multiplied times the derivative of the inside. So the mistake there is that we used a plus when we should be using a multiply. So this is good practice because I'm sure you'll have to do these complicated derivatives on the final, so we may as well be practicing that here.
Mm-hmm. Yeah. Okay.
What did we want the derivative to equal? I think you're getting confused about what you're writing down now. We didn't say that this integral was equal to the right-hand side. What do those ditto marks stand for?
Our answer from...
Well, what do the ditto marks stand for?
What's above?
And what is above?
Something else.
Yeah, they stand for the derivative of our answer. We wanted to take the derivative of our answer and make sure we got back to the original expression we were taking the antiderivative of. Okay, so let's scroll back up. One other thing with your check there, go to the first few lines of your check. Notice, so early on you used the constant multiple rule to take out the 1/5 times 1/4.
Right.
However, the way you wrote it, it makes it sound like you were factoring the 1/5 times 1/4 out of the c as well. So really there, you should, maybe you should have written out the plus c separately, or you can put in a right parenthesis and, well, maybe the best thing is to erase your second line and go straight to the third line. Let's just erase, erase the first line and go straight to it's hard to point them out, but erase the line that's above that. Do you see how that line is incorrect? Because it makes it look like the 1/5 times 1/4 is multiplying times the c, as well as the natural log.
Right.
All right. So maybe it would be better to go straight to the next line after that, to have that right in your notes. All right, like I say, that's worth practicing because I think you'll have to do those types of derivatives on the final, and it's also a good way to check your answers on these problems. So let's scroll back up then to the beginning. Well, we had a little trouble with checking the answer. But the process that you used for finding the antiderivative was excellent. This problem was harder than the ones we did before, and you had some trouble with it, but you did a really good job of just taking your time and working it out. You weren't really quite sure how to deal with the 5x in the denominator. You weren't quite sure how to deal with the 5x, but you thought about it for a while, and you came up with a very good solution, which is that 1 over 5x is the same as 1/5 times 1 over x. So that took you a little while to work out. You weren't quite sure about that. You tried a couple of different things, but you used a good process there. You just kept thinking about it until you came up with the best solution. So that was a very good process. You decided that 1 over 5x should be rewritten as 1/5 times 1 over x. That's good that you took your time and thought about it, and you came up with the best way to deal with that. So that was good. Let's see. One thing that you might have done there is point to the line that says 1/5 times integral 1 over x times u cubed dx.
Right here.
It might have been helpful then to rewrite that so that the x's are all close to each other. Okay. Then you can see more clearly what substitution you need to make. That's what we've been doing in the past. So you don't have to do that this time, but you could have rewritten that as 1/5 times integral u cubed times 1 over x dx, and then you can see more clearly what you're trying to solve for. So going forward, that would be a good process to use. Okay, so this was a harder problem than the ones we did before. You had a little trouble when you were checking your answer, but you used a very good process for figuring out the answer. This was harder than the ones we did before, but you took your time and you worked it out and you came up with the correct answer. So that was a good thought process. So I'll go back to my screen. That's good that you took your time and just thought about it until you worked it out. Why was it a good idea to say that u equals natural log of x? Well, what's the derivative of natural log of x?
1 over x.
And as you saw from how you rewrote that, that did appear in the expression. So that was the key that you figured out there for working that out. Good. Okay, try this problem.
Okay, so okay. I'll give this cosine, sine, v, plug u back in, plus c. So okay, so rewrite this as 1 over x times cosine natural log of x, and then we use u substitution. U equals natural log of x. So the derivative is the same as 1 over x, and we rewrote it, so x is on one side, and then we found a term we could sub in for 1 over x dx. We took the derivative with respect to u, sine of u, and the antiderivative with respect to u. Sine of u plus c, we plug u back into sine of u, that's what we get. Okay, now I'll check it.
Good. Let's check that. By the way, point to your next to last line of your solution.
Right here.
Good. What do the ditto marks stand for there?
What's above?
What is above?
Cosine of natural log of x over x.
So notice you didn't really, the last two lines are redundant, if you see what I'm saying. So all you don't need to change it now, but instead of rewriting the answer again, you could have just put integral of cosine natural log x dx on the left-hand side of that next to last line. So the point is, it's just good to rewrite what the ditto marks stand for in the last line of the solution to remind ourselves what they stand for. Okay. All right, but that's a good process. Let's check that.
Okay. Oh. Okay. So chain rule. Derivative of sine is cosine. Okay. Okay, cool. Matches up.
Okay, so it looks like we got that problem correct. Okay, good. So this problem was, again, a little bit different from the ones we did before. Not hugely different, but a little bit different. But you adapted the technique to figure out how to work that out. That's a good approach to adapt that again. Let's go back to my screen. The key here was to rewrite this like this. I think one of the key steps in the solution was to rewrite the expression like this. And this shows why we talked about this idea here earlier. Remember that when we saw this expression, we could rewrite it like this. So this is a basic algebra idea that we've used a lot today. The way that we can write this type of one big fraction as a bunch of multiplications with one variable in each multiplication. That's a trick that's turning out to be helpful on a lot of these problems. Why don't we try one more question here? Let's try this. Okay, this problem is similar to the ones we've done before. It does have one slight difference from the earlier problems. This is similar, but with one slight difference. But we should still be able to adapt our previous technique. So let's try to use our previous technique on this problem.
Okay. Let's see. So that writing sound usually means I did something wrong, so.
Dum dum dum.
Okay. 8x minus 5. Okay. So okay, so we have integral of sine of 8x minus 5 with the x, new substitution. Okay. I believe this is correct.
So for that last line, we can write what the ditto marks stand for.
Okay.
That's a good habit to be in.
Okay. Okay, so yeah. Okay, what's derivative? Derivative of cosine is negative sine. This is sine. Sine of u times 8. So this is sine of 8x minus 5. And this is okay.
So did the check show that we got it correct?
Yep.
What do you have written on the left-hand side of that final line?
The left-hand side is 1 over 8 minus cosine of 8x minus 5 plus
Okay.
c.
Now, if you go back and check your first line, you can see that you didn't quite copy that correctly. What's the left-hand side of the first line say?
Oh, yeah.
So that dash is not a subtraction sign, it's a negative sign.
Right.
Okay, that's always an important distinction to make. But anyway, you can see that you got this correct because you got back to the original function that you had taken the antiderivative of. Okay, that's a good method. So let's scroll back up to the beginning. Why did I say this one was different from the earlier problems? Well, just because the substitution you made here was u equals 8x minus 5. What's the derivative of 8x minus 5?
8.
Remember we said that you have to make a substitution whose derivative is also in the integral up to a constant multiple. Well, I just regarded this as a little bit different because here, in the past, the derivative has usually involved x in some way. Here, the derivative was just a constant, right? The derivative of 8x minus 5 is just 8. Well, that doesn't actually have to appear in the integral because it's just a constant. It does appear up to a constant multiple because 8 times 1 is 8. I don't know if that makes any sense. But anyway, in a way, these problems are simpler than the ones before because the derivative of the thing we're taking the substitution of is just a constant. Anyway, that did work out here correctly. You notice I was writing down something earlier. It was just because I wanted to remind you At first, when you did the substitution, at first you just wrote integral of sine u equals dx, and you hadn't written down what u stood for yet. And then you did that a moment later. But I just wanted to remind you, you always have to write down what u stands for. You should probably do that before you make the substitution.
Okay.
First, write u equals 8x minus 5, then make the substitution. People just make fewer mistakes that way. It didn't mess you up here, though. You were very clear in your mind about what you were doing the substitution for in this case. Let me go back to my screen. So here was the derivative that you were taking. You were trying to check your answer, and I think the first thing you wrote down was this. I think this is the first thing you wrote down. But this isn't quite right. We talked about this on the earlier problem. This makes it seem like the 1/8 was being multiplied by both the cosine and the c. When you write it this way, it makes it seem like the 1/8 was being multiplied by both the cosine and the c. Do you see why I would say that? Because the c is also in the parenthesis. So here's what you should have written instead.
Oh, okay.
You have to put the c separate to show that it's not getting multiplied by the 1/8. You should write the c separately to show that it's not being multiplied by the 1/8. So it didn't lead you to any mistakes in this case, but I think it's better to write it out like this. And let me show you something else on this. The next thing I would do here is this. Obviously, this derivative is 0. That is, you can take the negative out of the derivative too. You may as well make your life easier by taking the negative out of the derivative as well. Well, I don't know. I find this easier. I'll just show you this approach and then you can decide. Do you see why this is legal? Because this is really -1 times the cosine. So you can use the constant multiple rule to take that out of the derivative. I personally find that to be easier. Well, we'll see what you think. So this would be -1/8. Then you use the chain rule. What's the derivative of cosine u?
That's negative sine u.
For me, so what you did is you took the derivative of negative cosine u to be sine u. For me, this is simple, or maybe not for you. What's the derivative of 8x minus 5?
Just 8.
Can you see how can we simplify this expression now?
We can simplify this as -1 times negative sine of 8x minus 5, which is just sine of 8x minus 5.
Which is what confirms that we did this correctly. Okay, maybe you'll find this to be a better approach, but I wanted to show you this is an option. I just wanted to show you that just like you can take constant multiples out of derivatives, you can take negative signs out of derivatives. For me, it's simpler. The way you did it is okay too. Just to give you another option, so you can consider that. We can take negative signs out before we take the derivative. You can take the negative sign out, if you like, before you take the derivative. Like I said, there's nothing wrong with the way that you had done that. Okay, all right, well, we still have a ways to go with this technique. There's some other variations, but I think we made good progress on that for today. I think we're showing good understanding of the types of problems that we've done here so far. Okay, well, as usual, obviously we're going to want to try to build on this tomorrow, try to finish it if we can. Anyway, as usual, it'll be helpful before tomorrow to review what we just talked about so that we can move on to some new stuff. I do tend to think on these problems when you're reviewing them, it's also good to review checking by taking the derivatives. both because it's good to be able to check your answers, and because I think it builds better understanding if you check the answers, and also because you're gonna have to be doing long, tough derivatives like that anyway on the final, I'm sure, and we haven't practiced those for a while, so it's just good practice with taking derivatives, which you'll need for the final anyway. So when you're reviewing this, it's also good to review taking the derivative part to check the answers, because I think that's useful in a bunch of ways to us here.